Uh, right, thanks. Welcome everyone to this week's online analysis research seminar. This week we'll have Donggeun Ryou from Indiana University Bloomington, who's going to talk about sharpness of Mockenhaupt-Mitsis-Bak-Seeger theorem. Yeah.
Right. So yeah, let's get started. Okay, so first of all, thank you for inviting me, and thank you all for coming to my talk. I'm Donggeun Ryou, and today I'm going to talk about sharpness of the Mockenhaupt-Mitsis-Bak-Seeger theorem, and this is joint work with Robert Fraser and Kyle Hambrook. So first, I'll briefly talk about restriction estimate. If you're in harmonic analysis, then you'll already know well about this, but I'll just give a brief review about this. And then I'll give you the result in one dimension, and then I'll give you the result in full higher dimension. So this is the estimate. This is the main estimate that we'll consider in this talk. Mu is a positive Borel measure supported on a complex set in RD. And we consider the following estimate. The LP norm of F d mu hat, it is bounded by L2 norm of F with respect to the measure mu, and by this squiggle like inequality, I'm hiding some implicit constant dependent P. And where the F d mu hat is defined by the following Fourier transform with respect to the measure mu. Yeah. And by the way, just feel free to stop me if you have any questions in the middle. So if mu is a surface measure on the smooth manifold, then it is well studied. For example, like mu can be a surface measure on the paraboloid, cone, or moment curve. Then such estimates, they are related to dispersive PDEs. But in this talk, we're interested in when measure mu is supported on a fractal set. And a typical example can be a Cantor set. Right? So this is a very classical and well-known theorem, Stein-Thoma theorem. Mu is a surface measure on the d-1 dimensional paraboloid. Then for p greater than or equal to 2 d plus 1 over d-1, we have the following L to LP estimate. And also the range of p is optimal. If p is smaller than 2 times of d plus 1 over d-1, this estimate fails for a certain function f. And in the proof, the fact that paraboloid has positive Gaussian curvature played a key role. And if we consider a smooth manifold, then we can use some geometric properties of the surface like dimension, smoothness, and curvature. But if we try to obtain the similar result for fractal sets, then like not all geometric properties can be used. For example, like it's hard to think of what a corresponding concept of smoothness or curvature for fractal set. So this is a generalization which can be applied to fractal set. So it was independently proved by Mockenhaupt and Mitsis, except for the endpoint. And the endpoint result was later proved by Bak and Seeger. So this can be any general fractal measure in RT. It doesn't need to be a smooth manifold. So for the index, for index A and B between 0 and D, we assume two things. First, the measure of mu of ball of radius r that is smaller than r to the a. And when you take Fourier transform of mu, then it has certain Fourier decay, which is approximately 1 plus c to the power of negative b over 2. Then for p greater than p star, which is defined by 4d plus 4a minus 2b over b, we have the following L2 LPS. And recently, that was even more generalized by the concept of Fourier spectrum, and that was done by Carl and Jonathan Fraser and Orla. Yeah. So by the way, this person is a different Fraser because my coworker is Robert Fraser. So this result like reproves Stein-Thoma theorem because if mu is a surface measure on the paraboloid, then A and B are both d-1, so P star is the same range with the Stein-Thoma theorem. And in Stein-Thoma theorem, the range was optimal. So we can ask the same question. Is the range of P optimal in this? Let's say this is the generalized extension estimate from now on. So then we can ask if the range of P is optimal for this generalized extension estimate. So like the situation is a little more complicated because even if you fix A and B, there could be lots of measures which satisfies these two conditions. So we want to prove the following. First, we fix A and B, then like there exists many measures which satisfies this regularity condition and free decay condition. So this is what we really want to prove. For each P smaller than P star, we want to construct a measure mu, which satisfies this regularity condition and free decay condition for fixed A and B, but this L to LP estimate fails in the range. So such an example was constructed probabilistically first. So that was first constructed by Lava and Hambrook and Chen when the dimension, ambient dimension is 1. And later that was extended to some partial result in higher dimension by Lava and Hambrook again, when A and B both are between D-1 and D. And the first deterministic construction was constructed by Fraser, Hambrook, and myself in 1 dimension. And Donggeun Ryou and his student, they constructed another deterministic construction in 1 dimension with additional properties, which is interested in like incidence theory. Yeah. And we finally prove the range of P, prove that the range of P in this generalized extension estimate, a generalized extension estimate theorem that is optimal in all dimensions. So we fully solved the optimality in all dimensions, and also our construction is deterministic. But before we give more details about our result, I want to give you more context on this direction of research. So the first question was if we can construct an example where the range of P is greater than or equal to P star is optimal. But we can also ask, is the range of P optimal for all measures? And the answer is no, because let's say mu is a measure supported on a set of Hausdorff dimension alpha, where alpha is strictly smaller than D. Then the following is known. P, as though the following L to LP estimate can only hold when P is greater than 2D over alpha. And also it is well known that if alpha is small, and also, so combining with the generalized restriction estimate, we have the following result. If alpha is smaller than D, then we have the following diagram, so that if P is smaller than 2D over alpha, then the L to LP estimate cannot hold for any measure. But if P is greater than or equal to P star, then the L to LP estimate holds for any mu. And in the range where alpha is smaller than D, this 2D over alpha is strictly smaller than P star. So we can say the following. If we say P sub C, which is the critical P, in other words, that is the infimum of P such that L to LP estimate holds, then this critical P is between 2D over alpha and P star. So for certain measures, the critical P could be below P star. So such examples were constructed by many people. For example, like Chen and Seeger constructed. So these are examples when the L to LP estimate holds for the lowest possible index, which is 2D over alpha. And such examples were constructed by Chen and Seeger when alpha is D over K and K is an integer. And Shimuraki and Somala constructed such examples in 1 dimension when alpha is between half. And Lava and Wang, they constructed the example in nearly optimal sense, which means this L to LP estimate may or may not hold when P is exactly 2D over alpha, but it holds when P is strictly larger than 2D over alpha. And all these examples are probabilistic, so there's no explicit example known yet. Right, so let's put all this together. We have this critical P, and critical P can be between 2D over alpha and P star, and we have examples. So for certain measures, this critical P can be as low as 2D over alpha, and in certain situations, this critical P can be as large as P star. And our research is when the critical P is as large as possible. But actually, there are some examples when this critical P is strictly between these two numbers. In one of my previous work, I considered some fractal measure lifted to the parabola. In this case, the critical P was strictly between these two numbers. And this is the most recent research, Polasek and Rella. They considered when ambient dimension is 1 and alpha is 1, so that Hausdorff dimension is 1, but beta is 0 equals 0, which means there's no like free decay. But there's some like critical P, which is strictly between these two numbers. There's some non-trivial like extension estimate for this measure. So what does this say? Hausdorff dimension alpha and the exponent in the regularity A and the exponent in the free decay B, they are not enough to determine this critical P. So there must be some other determining factors that we don't know yet. And this direction of research is to answer that question. So we don't know the full picture yet, but we have certain non-trivial examples. And what we found is an explicit example when this critical P can be as large as possible. So if we have more explicit examples, then we can hope to see a pattern there. And that will contribute to find the determining factors for the critical P. All right. So let's talk about our result in one dimension. Yeah, because we first constructed such an example in one dimension, and then we extended to higher dimensions. So in one dimension, main tools that we used are well-approximable numbers and the Cantor set determined by arithmetic progressions. So this is a basic idea that Lava and Hambrook and Chan's paper used. And our idea also borrows some of their ideas from their papers. So let me explain those. They use two types of Cantor sets. First is a random Cantor set, and the second is a Cantor set determined by arithmetic progressions. So these are some like simple figure which explains what a random Cantor set is. For example, like in the first step, we can like divide the unit interval into 8 equal pieces. And then we choose like 4 out of 8. And for each chosen interval, we can subdivide this interval into equal pieces. And then choose 4 out of these equal pieces randomly. But in case of the Cantor set determined by arithmetic progressions, we choose Cantor set like which are separated equally. So these blue intervals, they are separated equally. And then for each chosen intervals, we subdivide this interval into equal 8 pieces and then choose intervals which are separated equally. So they use these two kinds of Cantor sets, but we wanted to construct an explicit example, like deterministic example. So we replace this random Cantor set by the set of well-approximate numbers. So let me explain what the well-approximate number is and why it is used there. So it has to do with the Salem set. So there is a concept of free dimension of a set E, which is defined as follows. When you have set E, then consider all the measures supported on the set E. And then we can evaluate the free decay of this measure. And we choose the measure which has the fastest free decay. In other words, we take the stream of the exponent of the free decay for all possible measures supported on the setting. That is called the free dimension of the set. And it is well known that Hausdorff dimension is always smaller than or equal to free dimension. So the interesting case is when Hausdorff dimension is same with free dimension, which is not always possible. And this is called the Salem set. So there are some simple examples. For example, a point is a zero-dimensional Salem set because it has zero Hausdorff dimension. And when you consider the direct measure, direct delta, then on the Fourier side, when you take Fourier transform of direct delta, then it doesn't have free decay. So point is a zero-dimensional Salem set. And another easy example is the paraboloid or sphere, because their Hausdorff dimension is d-1, and the surface measure has Fourier like exponent of free decay, which is minus d-1 over 2. But if you want to find some other examples other than this, then it's not as easy as it sounds. So it has been a question for a while, like for any alpha between 0 and d, where d is the ambient dimension, is there any alpha dimensional Salem set in RD? So such examples were constructed through so random construction was considered first. So such random construction was first done by Salem in one dimension, and Kahan finally constructed for every D. And after that, people found some explicit examples. And Kaufman first constructed explicit examples in one dimension, and that is where the set of well-approximate numbers is used. And Bloom extended this result to alpha, a higher dimension, when alpha is between d-1 and d. And after that, Hambrook, he constructed the explicit alpha dimensional Salem set in R2. And finally, Fraser and Hambrook, they constructed this alpha dimensional Salem set for everything. So now it is fully known that there exists an alpha dimensional Salem set in RD, and we know deterministic examples. So let's get back to the set of well-approximable numbers. So here's the definition. E of alpha, that is the set of x such that the distance between x minus x and r over q, that is smaller than q to the power of -2 plus alpha for infinitely many tuples of q and r. So this set itself is very often used in number theory, for example, in circle method. But Kaufman used this to prove the result in geometric measure theory and harmonic analysis. So he proved that the set of E of alpha is an 2 over 2 plus alpha dimensional Salem set, which means the Hausdorff dimension of E of alpha is 2 over 2 plus alpha. And so there exists a measure. There exists a measure such that mu hat is smaller than c to the power of 1 over 2 plus alpha. We ignore this epsilon because we can make this epsilon as small as we want. But we still need the condition on regularity. So we didn't use Kaufman's example directly. We also modified this measure in a way that we can also obtain the resultant regularity, which means the measure of an interval I that is smaller than length of interval to the power of 2 over 2 plus alpha. Right, so this is how we used this set of well-approximate numbers. And we also used the set of Cantor set from arithmetic progressions as well. So beta is between -1 and 1. And C of beta, that was used to denote the Cantor set determined by arithmetic progressions. So M sub k, that is a very rapidly increasing sequence. So we choose intervals which are equally separated. So yeah, so by using both Cantor set from arithmetic progressions and the set of alpha well-approximable numbers, on the union of these both sets, we were able to construct a measure with given regularity, which satisfies the given regularity and free decay for fixed alpha, fixed A and D. So this is about constructing the measure. Now we have measure which satisfies the regularity and free decay for given A and B, but we still need to show that this L2 LP estimate fails for P strictly smaller than P star. In order to show this, we need to go back to what we did on Stein-Thomas theorem, which is Knapp's example. So Knapp's example, that gives an example such that L2 LP estimate or extension estimate fails when mu is supported on the smooth manifold. So this is an example what happens on the parabola. For example, like if we use this f sub I as a test function, where f sub I is supported on the rectangle of size r to the negative f and r to the negative 1. When you take this Fourier transform of this fi, then it is essentially supported on its dual rectangle, so that the direction of the short side is the direction of longer side, which has length r, and the short side has r to the half. In that sense, these rectangles are dual to each other. When you test this to the extension estimate, then extension estimate fails when p is smaller than 6. This is what happened in the Stein-Thomas theorem. But again, we're trying to use this on the fractal sets. So in Knapp's example, only one component was considered. But in order to use this in fractal sets, we consider several components at each steps. So C of beta, that is the Cantor set determined by arithmetic progressions. And let's think of the kth scale. Then instead of one component, we consider this smooth function supported on this all components in the kth scale at once. So f sub k is not just one function, that is the sum of all these functions supported on the kth scale arithmetic Cantor set. So as k increases, there are more and more components at each scale. Then we use this as a test function. When you test this to L2 LP extension estimate, then if p is smaller than p star, this extension estimate fails. Okay, so this is what happened in one dimension. And now let's move on to the higher dimension. So first thing that we can try is to consider the cross product of the one-dimensional measures, and it doesn't work in higher dimension. So this is the wrong answer, and this is actually what I tried at first, and I realized that this is not the right way. So let's say mu is the measure constructed in one dimension, and let's say mu d, that is the product of lots of mu sub x1, mu sub x2, all the way up to mu sub xd. And when you take Fourier transform of this, then it's the product of mu of c1, mu head of c1, mu head of c2, all the way up to mu head of cd. And let's consider one direction only, where all the other coordinates are zero, and only c1 is non-zero. Since this was constructed from one dimension, a measure in R1, free decay, exponent of free decay cannot be larger than 1, because this mu is coming from the measure in one dimension. But here, we want to consider all higher dimensional, like we want to consider all possible indices of the free decay. So by this way, we cannot construct a measure with faster free decay in higher dimension. So this is not the right way to do when you consider all possible indices of A and B. Instead, we used like explicit examples in known explicit examples in higher dimensions. So in one dimension, we used a set of well-approximate numbers because it was an explicit Salem set in R. And as I mentioned earlier, Fraser and Hambrook, they constructed explicit examples in higher dimensions. And we used this. in our construction. Also, we modified the construction in a way that we can also obtain the regularity. And also, we didn't directly like apply their construction because our construction is slightly different from the Fraser and the work of Fraser and Hambrook. So we were also able to simplify a lot of parts of their argument. Right, so let me talk more about the explicit example, explicit theorem set in RD. Actually, that needs a little knowledge of algebraic number theory. So this is sort of like crash course on algebraic number theory. E of alpha, that is the definition of the alpha, well, approximate numbers. And natural generalization that we can think of would be the following. E of tau. The reason why I'm using tau is just because we use that in the paper. So E of tau, there is a set of X in RD, and they seem very similar except for now we consider like Q comma R, where Q is in ZD and R is in ZD. So it seems like a natural generalization, except that like what R over Q is, because Q and R are like vectors in integer lattice. So it's not very clear what does it mean by integer vector divided by vector. Because in one dimension, R and Q are numbers, so R divided by Q, that's quite obvious. But now R and Q are vectors in higher dimension. And this is the main idea that how they like go around this obstacle. When you have 1, 1, then we can identify this with certain element in number field. For example, like let's say complex numbers. Then 1, 1, that could be identified with 1 plus alpha, and 1 minus 1, that can be identified with 1 minus 1, 1 minus I. Then division between complex numbers, that is well defined. So 1 plus I divided by 1 minus I, that is just I. So that 1 minus 1 divided by 1, 1, divided by 1, negative 1, that can be identified by 0, 1. And this is idea which can be applied to all the higher dimensions. So this is the full generalization. So K, this is on like field extension of Q of degree D. Such a field extension exists for all D. So we can think of like all possible higher dimensions and choose the field extension that you like. And also K, that is the ring of integers of K, and B, that is the integral basis for K. So here's an example if we apply this to like complex numbers. For example, like let's say K, that is the field extension of Q of degree 2, which is given by A plus BI, where A and B are complex A and B are rational numbers. Then the ring of integers, that is A plus BI, where A and B are integers. And we can choose integral basis, which is 1 and I. And then we can identify A comma B with A plus BI. So when you have Q, which is the vector whose elements are rational numbers, Q1 to QD, then this can be identified with an element in the field extension, which is the summation of Q sub I times of the elements in the integral basis. By this way, we can identify the ring of integers with the integer lattice and the field extension with Q to the D. And we can use the distance like Euclidean distance for the distance in this space, so that the length or the size of Q, that is the just little L2 norm of the elements, Q sub I. Right, so this is the construction that we really consider. Actually, instead of like R over Qs, where R and Q are vectors, we consider the ideal. So for each ideal in the ring of integers, we consider the inverse ideal. inverse ideal, that is the elements in the field extension, such that the A times of this ideal is in the ring of integers. And we also consider the norm of ideal, which is the size of ring of integers quotient, the ideal I. Then we define E of K B tau. So this is the set of X in Rd, such that the distance between X and I inverse ideal of I, that is smaller than the norm of ideal to the power of negative tau plus 1 over D for infinitely many ideals in the ring of integers. So this can be a natural realization of the set of well-approximate numbers in the following way. Let's try to use this in one dimension. When D is 1, then we don't need field extension. We can say K is exactly the set of rational numbers. Then naturally the integral basis can be just 1. If we choose one integral ideal, if we choose one ideal in the integer ring, then that'll be like q times of integers, like 0, q, 2q, 3q, and also negative q, negative 2q. So multiples of q. Then the inverse ideal, that'll be the multiples of 1 over q. And the size of this interval, the norm of this interval, that is just q. So when you replace every terms in this definition of E of K B tau in terms of some more easier language, then that exactly reproduce the definition of E of the set of well-approximate number. So that exactly becomes the set of X such that the distance between X and R over Q is smaller than Q to the power of negative tau plus 1 for infinitely many R comma Q in the integer lattice. So this is an example in one dimension, but by using any field extension of Q in higher dimension, we can generalize this to all higher dimensions. Right. So we showed that this set is a Salem set, which means there exists a measure mu on this set such that the Hausdorff dimension is 2D over 1 plus tau. And there exists a measure. And when you take the Fourier transform of this measure, then the Fourier decay is exactly half of this Hausdorff dimension. And we also constructed the measure in a way that it satisfies the regularity. So the measure of ball of values R, that is R to the power of the exponent, which is exactly the same with the Hausdorff dimension. Yeah, so this plays the same role of set of well-approximate dimension as set of well-approximate number in one dimension. And in order to consider the corresponding thing of Cantor set determined by arithmetic progressions, we considered ideals. So what is good about ideal is because in the perspective of our problem, the role that ideal arithmetic progressions plays is same with the role that ideal plays. They have sort of lattice structure in terms of our problem, but it has less things to think about. Because when you consider lattice in RD, then there are more parameters to think about. For example, let's say the axis of lattices are parallel to X and Y, then we need to think of the common difference between elements in X-axis, and we need to think of the common difference between elements in Y-axis, and they don't need to be equal. Also, when you have just lattice, then the angle between axes may not be exactly the right angle. So there are more parameters to think of if we consider lattice in RD, but if we consider ideals, then there's only one parameter to think of, which is the norm of ideal. By controlling the norm of ideal, we can control all the estimates of this, all the estimates related to this ideal. So this is the set that we consider instead of arithmetic progression. First, we choose an ideal in the ring of integers. And at each scale, we consider a neighborhood of the elements in the inverse ideal J with properly chosen norm. So it behaves like lattice, but with only parameter to consider, which is the norm of J. So yeah, by this way, we consider the set that corresponds to the Cantor set that corresponds to the Cantor set determined by arithmetic progressions. And considering both of these sets, like Cantor set determined by these ideals and this E of k be tau, we were able to construct a measure which satisfies the given regularity and free decay condition for fixed A and B. Also, we consider a smooth function f sub k supported on the Cantor set determined by the ideal. And when you use this as a test function, then it again fails the L2LPS maze fails when P is strictly smaller than P star. Right, so let me give you a little more detail about the estimates or some arguments that we used in this proof. So when you're using E of alpha set of well-approximable numbers in one dimension, the two facts play key roles. First, the number of primes smaller than m is smaller than m divided by log of m, which comes from prime number theorem. And we also used, so this is to count the number of like intervals when you're constructing the measure. And if p is a prime and s is an integer, then we have the following exponential sum. So we evaluate the following exponential sum of e to the 2 pi I and s divided by p. Then the result is always one of the two, p or 0. If s is divisible by p, then exponential sum will be p, since there's no cancellation at all. And otherwise, the estimate will be always 0 because of cancellation. So we use this to evaluate the free decay of the measure that we constructed. So yeah, to be more specific, this is the building block of the measure that we constructed. Like m is a large constant, and p of m, that is the set of prime such that the size of prime is approximately m. Then we constructed a function, smooth function, which is supported near r over p's. Yes, to normalize this function, we needed this prime number theorem. And to evaluate the Fourier transform of this, we needed the exponential sum, which is above. And this is what happens when you consider in higher dimension. So as an analog of prime number theorem, we also have Landau prime ideal theorem. If you consider the number of prime ideals such that the norm of ideal is smaller than m, then it has the same estimate, m divided by log of m. And as an analog of the exponential sum in one dimension, we also have the following exponential sum in higher dimension. So I is a prime ideal in the ring of integers, and R of I, that is the complete set of representatives of the inverse ideal of I. And S, that is the element of ring of integers, which can be identified with an element in the integer lattice. So the exponential sum that is done in Euclidean space. So this R dot S, that is just the inner product the usual inner product that we use in RD, which that we often use in Euclidean space. There is no like number theory structure here. Only number theory structure here is just R of I. This I that is chosen from the ring of integers, and we just consider elements in this set of Ri. Other than that, all the calculation here that is done in just RD, Euclidean space. But if these elements R are chosen from R of I, then there's the following structure. So I'm not going to explain what delta inverse is and T is, but they are fully determined by the choice of the field extension. After you choose the field extension, they don't change. They always, like, they are independent of our choice of I or choice of other parameters. But there is some certain set, which is T of delta inverse of I. And if the element S is in this set, then there's no cancellation at all, so that the exponential sum is the size of a norm of ideal. And otherwise, there's cancellation so that it is always 0. So we also use this to evaluate the size estimate of the Fourier transform of a measure that we constructed. Yeah. So as in one dimension, this was the building block of the measure that we constructed in higher dimension. So this is the sum of smooth functions, which are supported near R, where R is an element of the inverse ideal of I. Where Q of M, that is the set of prime ideals, such that the norm of ideal is approximately m to the power of d. So Landau prime ideal theorem that was used to normalize the measure, and the exponential sum that was used to evaluate the Fourier transform of this measure. Right? So let me summarize this. There is a generalized extension estimate, which can be applied to fractal measures. And we proved that the range of P here is optimal. In other words, there exists a measure P. So for given A and B, there exists a measure which satisfies given regularity and Fourier decay condition. But L2 LP estimate fails when P is smaller than P star. So in one dimension, we use the set of well-approximate numbers and the Cantor set determined by arithmetic progressions. In higher dimension, we use the finite field extension of Q to use some ideas in explicit Salem set in higher dimension. And also you use prime ideals instead of prime numbers. And also we use the exponential sum over R, which are the elements of the inverse ideal. Okay, so I'll stop here and thank you for listening.